All right, welcome back to, I guess it's lecture 17. Someone wrote on the board. Not sure if that's accurate or not, but that's what it says. And we are doing chapter 19, sampling. Sampling distribution of a mean. Thank you very much. I don't like this one. The sampling distribution of a mean. So up until now, in the last few chapters, we have been focusing our attention on proportions. We did one proportion, we did two proportions, we did confidence interval proportions, we did confidence interval for two proportions. Hypothesis testing for proportion and hypothesis testing for two proportions. The other quantity that we'll be studying in this course. What? Huh? What? What? What happened to what?
Is this worse than your high school class?
I don't think it could be worse than that, but it's pretty bad. All right, so the other quantity that we're considering is the mean of a population. So simple examples, the average height, the average weight, the average mass of a grain of sand, the average luminosity of a star. There's many situations where we are concerned with an average, not a proportion, but an average. And we want to know what that average is. I will never know the average luminosity of every star in the universe for the simple reason that from here on Earth, we can't see every star in the universe. Even amongst those that we can see, how many years has the light from those stars been traveling to Earth? Millions, billions in some cases. Those stars could be dead by now. When you wish upon a star, the star might be dead, like your dreams. So the point is, we will never know the average luminosity of the stars in the universe. But what I can do is one of two things. I can either get a confidence interval for them and say that, okay, I don't know the true value, but it's somewhere between here and here with 95%, 90% confidence, whatever the case may be. Or I can do a hypothesis test. Someone can come along and say, well, I believe the average luminosity is 17 lumens. I'm not even sure if that makes sense. I don't know what a lumen is exactly. I just know it's a measure of brightness. And you might have.
Hi.
So you might have a hypothesis test where the alternative is no, it's greater than that, no, it's less than that, or no, it's not equal to that. So the calculator at the end of the day will do all the work for us like it always does. But it's important to understand the ideas behind it. And we start with another version of the law of large numbers. We had a law of large numbers before, do you recall?
The large number law?
Oh, I just don't feel like I can get any dumber than I come to class. So yes, the law of large numbers, the large number law. Could someone remind me, please, what the large number law was? Yes.
Like the more numbers you use,
Sorry, what?
the more numbers you use, the more accurate that your data will be. So if you do it,
Yeah, keep going.
so if you, let's say you want to do a survey of 30,000 out of like 100, that will be more accurate than 300. But like
I like what you're saying, but when you said 30,000 out of 100, I'm a little curious how you're going to obtain that, huh?
100 out of 30,000.
That makes a lot more sense. Okay, but the distinction I want to make is that the law of large numbers that we did last time dealt with proportions. We said as the size of your sample increases, the sample proportion approaches the true proportion. Now we're doing a law of large numbers in relation to mean, but it's the same idea. As the sample size increases, Your sample mean will approach the actual mean. So the same idea. I'll do it in shorthand as n goes to infinity. As the sample size gets really, really, really large, x bar, which is my sample mean, gets closer and closer to what? To what? X is not the symbol that we use for the population mean. Mu. Mu. Right? The sound that a French cow makes. Mu. Right? So it's my favorite joke. Don't mess. Don't mess. So the law of large numbers says as the sample size increases, the sample mean approaches the population mean. Why does that happen? Why is the law of large numbers true? Yes?
Oh, I mean, I thought you were asking.
No, I was being rhetorical, but go ahead.
Well, but you can.
No, please go ahead. No,
I mean, like,
no, please go.
alright, so, like, like you said, so the bigger the thing gets,
The bigger the what?
the thing.
The thing, yes.
The sample.
You don't say a word. Yeah, keep going. Go ahead.
You
can't do it.
The bigger the sample gets, the closer you get to the.
I understand. So why should that be the case?
That's because you're getting like more closer to the actual like population.
But why? You're just repeating it. The question is why? Mathematically, why?
Oh, well, because bigger numbers means better.
Yes, but I'm looking for the why bigger numbers means better. Yes.
Want the nerd definition?
Yes, the nerd definition.
As the limit of x bar approach.
No, you're just repeating it with your, no, that's not what I'm looking for. Yes,
Is it because the percentage increases in,
No.
like,
it's because the standard deviation, the spread goes to 0. See, when you have a sample, let's say a normal distribution, which looks like this, right? It's a bell curve. It's going to have a certain standard deviation. When you take 2 at a time, 3 at a time, 4 at a time, 5 at a time, 10 at a time, 100 at a time, and so on, each one will have a smaller and smaller standard deviation so that my curve gets steeper and steeper and thinner. And since we know that 99.7% of the data is going to be within 3 deviations of the mean, if that's this far apart, that's a pretty wide spread. But if the deviation gets small so that 3 deviations becomes this, now 99.7% of the data is going to be all in here. And we're much more precise of a value. It's not magic that this happens. It's not just intuitive that it happens. It's mathematical. The reason why the sample mean approaches the true mean is because the spread of values shrinks to 0. And if there's no spread of values, we're essentially getting the same value every time. And if we're getting the same value every time, that's the value that we're looking for. This is the basis behind the law of large numbers. The actual proof requires some more advanced mathematics that we're not going to do, but this is the idea behind it. So we know we'll be given that X is normal with some mean and some standard deviation. So I tell you that we have a distribution labeled as capital X. And I tell you that this can be modeled by a normal distribution with some mean mu and some standard deviation sigma. When I give you this information, in theory, I'm giving you everything there is to know about the distribution. The n tells me that it's bell curve. It's a normal distribution. It looks like this. The mu tells me where the center is at. And the sigma tells me the spread. So when I know that information, I essentially know exactly what my curve looks like. I know the center right here is mu. And I know that if I go to the right to the point of inflection, that's a distance sigma in both directions. So 1 deviation in either direction. How much of the data falls within 1 deviation of the mean if it's normal? 68%. And if I go 2 deviations out, 95%. If I go 3 deviations out, 99 points. I know so much information just by being told that X is normal with mean mu and standard deviation sigma. But what if now I don't want 1 at a time? I want 10 at a time, and I want you to average them and give me that number. So let's think about it for a second. Suppose I'm curious. I'm looking for the average height of every American. That's my goal. What is the average height of every adult, 18 and over, every adult American? How conceivable is it that if I go to the mall, let's say, and I wait for the 100th person to round a corner, that 100th person is 6'4"? Is that an impossible event? Would you be surprised if it happens?
Yes.
Yeah, well, you'd be a little surprised because most people are not 6'4". But would it shatter your entire conception of how the universe works if someone 6'4" came around the bend? No. Well, let's say I do this 100 times. I wait for a number of people to come around and I say, okay, next one comes around. Oh, 6'4", 6'2", 6 foot this, 5 foot this, and the average was 6'4". If 100 people at random were measured and their average was 6'4", how shocking would that be? A lot more shocking than the original. Because for 100 people to have an average of 6'4", essentially all of them have to be really, really tall. And that's just not really likely unless I happen to go to, like, you know, basketball tryouts or the anti-jockey society or something like that. Okay, so the point is that the reason why it's so shocking is because while 6'4" might appear here on a regular normal curve, if I do instead the average of 100 people, let's say, then 6'4" is in the same location. But how many sigmas out is it now? Huh? A lot more. The event is the same location on my axis, but relative to where the mean is and with the size of sigma, that's why it's a lot less likely. So what we're going to do is we're going to come up with a distribution for X bar. What is the X bar distribution? And the answer is, it is also normal. So if I decide to take a sample of some size, let's say it's 10, 100, whatever the case may be, and I graph that distribution, it will also be normal. It will have the same mean, the same center, the same peak, will be exactly the same point. But now what changes? What's the only change that we're going to make is the spread is smaller. The bigger the sample, the smaller the spread. And the spread is given by sigma divided by the square root of the sample size. So if I were to quadruple the sample size, not quadruple, sorry. If I would take a sample size of size 4, rather than 1 at a time, I would do 4 at a time. How would sigma compare for the 4 at a time situation versus the 1 at a time situation? It will be half as big. Because if n is 4, the square root of 4 is 2, so you're dividing by 2. So if the original sigma was, let's say, 3 inches, then if I do 4 at a time and average them, that sigma will be 1.5 inches. So by raising the sample size, we lower the spread, we tighten our curve, and as a result, an event here, which might have been somewhat likely for 1 at a time, becomes unlikely for 4 at a time, or 10 at a time, or 100 at a time, and so on.
You said the bigger the spread, the smaller the size.
No, well, first of all, it would be in the opposite order. The bigger the sample size, the smaller the spread. And what you said might be true, but it's just the cart before the horse type thing. Huh? Who's choking? So why would he leave? This is a good occurrence. Okay. Now, Ariana, how are you? Good. Were you not supposed to play a game today? Because I had you down for one. I see. Well, I wish you the best of luck. Okay. So let's do an example. Let's do an example. Can I erase what I have on the board so far? Okay. Okay. So this is example 19.4 in the book. It says, if we measure the DMS odor thresholds of individual adults, I'm not exactly sure what this is, but if we measure something, the values follow a normal distribution. So we have X is a normal distribution with mean mu equals 25 micrograms per liter. I'll just write the numbers and not worry about the units because we're focusing right now on the numbers. So mu equals 25 micrograms per liter and sigma equals 7 micrograms per liter. So we have whatever this thing is, follows a normal distribution whose center is at 25 and whose sigma is at 7. So just a quick question before I even read their question. How many of my data points would I expect to appear between 18 and 32? 68%, because 18 is one sigma down, 32 is one standard deviation up. And we know that 68% of the data. Okay. 68% of the data is going to appear within one standard deviation. Now, it says take samples of size 10. So take samples of size 10. Not just one sample. Take 1,000,000 samples of size 10. Take lots and lots and lots of samples of size 10. Do we expect, because X itself is distributed, which means all of these values are possible, the ones in the middle, of course, more likely than the ones on the side, but all of them are possible. Do we expect to get the same average every time from every one of our samples? Is every one of our samples going to give exactly the same value as the average? No, right? Just like the original distribution has lots and lots and lots of values, our averages are going to have lots and lots and lots of values, which means that the average that we get from 10 at a time will have its own distribution. What will this X bar distribution be? What will the shape of it be?
Normal.
It'll be normal. If the original distribution is normal, the X bar distribution is also normal. What is the mean of my distribution going to be? What do I expect the average of all my samples to be? Also 25. And what do I expect the standard deviation? 7 over the square root of 10. And the square root of 10 is about what? A little more than 3, a little more than 3 point something, which means my sigma has dropped from 7 to 2 point something, 2.21. So my spread, the width of my curve has shrunk. So if I ask now, what percent of my data will be between 18 and 32, has it gone up or has it gone down? It's gone significantly up. Let's again see why. If I graph my original, here's my original curve. So here's 25, here's 18, here's 32. We have roughly 68% of my data falls between those values. This is for the original distribution. Now I'll do it in red, but how far do I go sideways to get 1 sigma now? 2 point something, which means my new 1 sigma is this. So 68% of my averages will fall between here and here. So if I go all the way out to 18 and all the way out to 32, I'm obviously going to have more than I had if I only went this far out. In fact, what's my new curve going to look like? It's going to look like this, something like that. So if I go 18 to 32 now, I'm missing, right, just a little bit on the sides. I've accumulated a lot more. Does that make sense? This is why a non-outlier, one at a time, might be an outlier when I do an average. And this is why we take averages, so that we're more inclined and more confident that our values are going to be somewhere near the middle. Does that make sense conceptually? Okay, so we're going to need this to do confidence intervals and hypothesis testing. But before we do that, we need what is arguably the most important theorem in elementary statistics, at least for computational purposes, and that is the central limit theorem. The central limit theorem. At the end of the day, the central limit theorem is what allows us to actually do the majority of our statistical inference that we do in a statistics class. Because unlike the last example, where you knew that it was normal, and therefore X bar is normal, what if the original distribution is not normal? What if I have anything other than normal? What if my shape looks like this? That's certainly not normal. What if it looks like this? That's certainly not normal. All right, there's lots of shapes that are not normal. And if the original distribution is not normal, then it doesn't seem reasonable necessarily that your X bar distribution is going to be normal. And yet the central limit theorem says, don't worry, it will be under one condition. So the central limit theorem essentially says is no matter what the distribution, well, almost, no matter what the distribution of X is, X bar is approximately normal if the sample size is large enough. X bar is approximately normal if n is large enough. This is essentially what the central limit theorem says. It's not the technical word for word definition that you'll find in the book, but it's the intuitive definition. Yes?
What's defined as large enough?
What's defined as large enough? So if you recall near the beginning of the semester, I loaded up an applet when we were on Zoom called, and I would recommend looking at it again now that you have a little more experience with the class. But the Google link, I don't know the website by heart. So the way I find it is I do a Google search for central limit theorem applet. And it's the first link. And if you recall, we had lots of weird distributions on there. And as we raised the sample size, the shapes changed. And in all cases, they ended up being a bell curve. Sometimes it only took n to be 4 or 5, and it looked like a bell curve. Sometimes 10, sometimes more. In general, to be safe, make sure n is greater than or equal to 30. This is the general number that I found in most textbooks. Some textbooks use 40. I've seen numbers around 30. And I would recommend if you're ever out there in the world and you're actually a statistician and you're actually deciding, should I use the central limit theorem in this case? Then you should always check on a case-by-case basis based upon your data, whether or not your data appears to be normal and therefore the central limit theorem is appropriate. But for the most part, n is greater than or equal to 30. You can use it. And when you do, X bar is about normal with the same mean mu as the original and the same formula sigma over the square root of n, where X, right, the original distribution is n of mu sigma. X bar is n of mu. Sorry, don't erase this n here. This is the whole point of this, is that we don't know what it is. Right? We have no idea what the distribution is. That should be a question mark. But we do know its mean and sigma. So we don't know what the distribution is, but it has a mean and has a sigma. If I take 30 more at a time, if I take my samples to be greater than or equal to 30, then X bar will be normal with mean mu and sigma over the square root of n as its standard deviation. Yes,
What's the difference between X and X bar again?
x is 1 at a time, x bar is an average. Right, so you do 10 at a time, x bar is your distribution for your sample. It is your sample distribution, your average distribution. In other words, if I have the room here of all these people, everyone's heights are different, I can plot them, it would have some kind of graph, right? If I take 2 people at a time, average them and plot that, that would be my X bar graph. I'm plotting averages versus plotting the original data. Okay, because if in the original data, right, one of the ones, if you remember on that applet, the distribution looked like this. This was the distribution. Was very likely to have a result here in the far left and very likely to have a result here on the far right, but not so likely to have a result in the middle. This was X. This was 1 at a time. But what if I take 2 at a time and I average them? Well, if I take 2 at a time and I average them, would I expect to have many in the middle?
Yes.
Yes, because now I'll have a bunch from the left and a bunch from the right as my pairs. So the distribution will look more like something like that, where it's high on the wings because it's highly likely that I'll get 2 here or 2 here, but also highly likely that I'll get 1 here and 1 here that averages to a high value here. So if you have a computer handy, I would recommend loading up right now on your computer, because I'm on a Zoom, for you guys. But if you load up as a Google search, central limit theorem applet, I would recommend doing this right now. You all have phones. So take out your phone, use your computer, whatever the case may be. Look at central limit theorem applet. I'm pretty sure it's the first link. It's the one with the numbers, lots of numbers. Yeah, you have the right applet. Yeah, the one with the numbers, the very first link. Click the distribution that looks like that, which is number 4. Do 1 at a time. Have it generate 1. Well, you did 4. You're still on 1. Have it generate 1 at a time. Draw, and that should have a sample that looks like that. But now switch it to 2 at a time. So you got to hit the increase button, and I draw it again. And you should have a distribution that looks like peaks on the left and right, and it's even better. So if you don't have it, so this is 2 at a time now. You can see here, I'll show it up here so people at home can see, but you see here that by doing 2 at a time, you now have peaks on the left and right, and in the center as well. And in fact, the peaks on the left and right aren't all the way on the left and right, because to have one on the very far left would require both to be on the very far left or the very far right. And even though that's possible, it's not very likely, which means it's not going to be as high as around here, and around here. And then if you go to 3 at a time, 4 at a time, 5 at a time, how high do you have to go before it starts to look normal? What's your N? 20. Okay, so someone do 15, someone do 10. Does it look normal in those cases? Even though it starts out as basically as anti-normal as can possibly be, with the most on the wings and nothing in the middle, what's the sample size where it starts to look about normal? 10. Even by 10 it is. So 30 is basically saying, just be really, really safe, wait for 30. But we see here, even in a case where it looks really, really not normal, as anti-normal as it gets, 10 is already enough to make it look normal. And pick another one.
Like 8, 2, 7.
I'm sorry?
7 also. Or
Even by 7 it is. Pick another one that looks very anti-normal. Your choice. Don't pick the one that actually is normal, of course. That would defeat the purpose. But any of the other ones, and see what kind of sample size you need before it starts to look normal. It should start even as low as 10, no matter which of the cases you do, it should be enough to look normal. So 30 is just like basically to be safe. Of course, if the original one was normal, then X bar is automatically normal. That's actually part of the central limit theorem too, that if the original one was normal, then you get normal for the ride. The X bar is normal no matter what the sample size is. In those cases, you don't have to wait for 30. If in the problem it says you're given a normal distribution, then automatically your X bar will be normal as well. And you don't have to worry about having a large enough sample size. But that applet is really, really, really useful and very illustrative. Okay, so let's do an example now. So this is example 19.7 of the book. And this shows you, by the way, this example shows you even in a very relatively simplistic situation, how useful statistics can be for anyone who one day plans to run their own business. I don't think this is not science statistics for business majors, right? This is for science majors.
Yeah.
Oh, it is business majors. Okay, even better. So how many of you hope to one day run your own business? How many hope to hire me one day when you run your own business? Okay, so this simple example shows how useful statistics can be. The time and hours that a technician requires to perform preventative maintenance on an air conditioning unit is governed by the exponential distribution, whose curve is given in some other problem in the book. Now, we've never covered exponential distributions, so we don't know what they look like. I'll draw one for you, just to have as a reference. But your typical exponential distribution looks like this. Okay, this is a distribution that's defined only on the positive numbers, 0. Unlike a normal, which goes to infinity and negative infinity in both directions, the exponential distribution is often used for lifetimes, how long something lasts before it breaks down. And you can't have, I mean, just think about it. A normal distribution goes to negative infinity. You obviously can't have negative time. It doesn't make any sense. So most things will break down early, and the longer it goes, things will still break down, but fewer and fewer of them will last longer and longer and longer. This is the exponential distribution. So, well, that's a polynomial. X squared is exponential by e to the x, or e to the negative x, more specifically. Well, the x itself, in theory, for an exponential could be negative. I mean, the graph of e to the negative x does continue on the other side. We just ignore that part for this particular context. It says the exponential distribution arises in many engineering and industrial problems, such as time until failure of a machine or time until success. The mean time, the average time, is 1 hour. This is the average time that a technician requires to fix a machine is 1 hour. So mu, the average, we are told, is 1 hour. This is not a, what is mu? I don't know situation. Let's form a confidence interval or hypothesis test. No, we're telling you the average is 1 hour. And sigma is also 1 hour. So not only is the average 1 hour, but sigma is 1 hour. Now, the normal distribution has the property that if you go 1 sigma in either direction, it's 68%. That is not something that you can carry over to other distributions. It is only true for the normal distribution. So if I asked you how many times it will be between 0 and 2, 1 sigma this way, 1 sigma that way, the answer is not 68%. You'd have to do it in a more sophisticated method. There is something called Chebyshev's theorem, which is kind of like the 68, 95, 99.7 rule for other distributions or all distributions. But in general, we're not going to learn that. Just don't make that mistake. Your company has a contract to fix 70 of these units in an apartment building. So your company is sending an electrician or a technician, whatever the case may be, to monitor it, to check and to do a maintenance on 70 units, each one of which takes 1 hour on average, with an uncertainty, a spread of 1 hour. Now, you're sending this guy or this girl over to fix these things, right? You have to schedule time. How much time do you allot to fix these units? You might say, well, I got 70 units and each one takes an hour. So I will send them there for 70 hours of work week time. But now you're not taking into account that there's an uncertainty involved. What if the 70 hours have come and gone and he hasn't finished all of them? Or on the other side, what if he finishes way early and now you're paying him to sit around and do nothing? We want to kind of have an idea of how long we expect this job to take. So, is it safe to budget an average of 1.1 hours for each unit? Is it safe? Is it safe to budget 1.1 hour per unit? That's the question. In other words, from a mathematical standpoint, we're going to rephrase this question in terms of probability. What is the probability that it takes a technician less than 1.1 hours per unit? If it's 99%, if the answer is there's a 99% chance that it takes less than 1.1 hours per unit, would you feel comfortable sending them along for that amount of time? What if it's 50% chance? Okay, well then somewhere in between, there's like a cutoff where you as the business owner would be comfortable. Let's find that value. Is 1.1 enough? So our question is, what is the probability that X bar, the average, is less than or equal to 1.1? What is the chances that our average value from our 70 takes a value less than or equal to 1.1? How likely is it that our average will be less than or equal to 1.1? Now we can go directly to the calculator for this. We just have to know where to go. Where do we go on our calculator? Which we've learned a bunch of stuff in the calculator by now. We've done confidence intervals, we've done hypothesis testing, we've done normal CDF, we've done inverse normal. That might be it, actually, now that I'm thinking about it. But is one of those the right one to use? And if so, which one is it? Which one is the one that we want to use? And whatever one we pick, we also want to make sure that we know what inputs to use. So which one are we going for? Which one is it? Inverse norm is what you use when you have the probability and you want to go back to the value. Do we have the probability here, or are we looking for the probability? We're looking for it. Do we have the value? So which one do we want to use? There's not a hypothesis test. We're not testing anything here. There's no null, there's no alternative.
Normal PDF.
Not normal PDF. We never use normal PDF. We never will use normal PDF. We use normal CDF. And if you go, because, and how do I know, by the way, that I can use normal? Isn't this exponential? It's greater than or equal to 30. And because it's greater than or equal to 30, even though the original distribution is exponential, I don't care, because my rule of thumb is that as long as n is greater than or equal to 30, I can treat it like it's normal.
So what are we trying to find?
The probability that X bar is less than or equal to 1.1. What's the likelihood that my average value from all 70 is less than or equal to 1.1 hours per unit?
Okay, but if you were to say just on the calculator, like, are we just trying to, is this how you find the probability of anything?
Not anything. I mean, it's a case-by-case basis. When it's a normal situation, which the central limit theorem tells me that it is, I go to normal CDF. And when I go to normal CDF, it's going to ask me for a bunch of stuff. What's the lower? Negative, lots of nines, negative infinity. What's the upper? 1.1. What's mu?
One.
1. What's sigma? What's sigma? What's sigma? You guys are talking like I'm deaf. I've asked 4 times and I've gotten 4 wrong answers. And what I mean by that is for lots of answers. What? 1 over the square root of 70. Because remember, the distribution for x bar has 2 parameters. The mean is the same mean as the original. But what is the sigma for x bar? Look at your notes. If you wrote it down, hopefully you did. What is the sigma? I'm looking at you. What is the sigma for x bar? 1 over the square root of n.
Why is it lower than -999?
Because it says less than or equal to 1.1. Technically, you might be a little justified in saying, wait a second. I know we're treating it like it's normal, but you can't go lower than 0. I mean, time is time. Well, you'll find that the difference is negligible anyway. And remember, this is only an approximation, so it's close enough. So I paste, I kept, oh, I was in the wrong spot. Mother crapper. Are you rooting it for me? So what is it?
0.119.
0.7986. 79.9%, about 80%. If you got something different, then you did something wrong. Not that I'm surprised with you. Huh? You got an error message. Then you probably did something very wrong, huh?
What are you plugging in?
So you go to normal CDF. For your lower, you're plugging in negative infinity. Normal PDF, which we never use. If I had my way, we would take it off the calculator altogether. No. Huh? Use what? It's not that it's useless, but it's useless for you.
Wait, so like when would we have?
You will never in this class use normal
I mean,
PDF.
like what class would we have?
You take a 400 level statistics class, you might end up using it. So what do we get? What do we get?
798.
So there's about an 80% chance. There's about an 80% chance that your technician will finish if your technician budgets 1.1 hours per unit. As the business owner, would you be comfortable sending your technician out for an 80% chance of success? Well, no, be realistic. Be realistic. What's better for you? Having that technician have extra time that he's not using or she's not using, or not having enough time to do the job?
An hour and she's a good job.
Having extra time, huh? What? If what? And then you get sued or whatever the case may be. Don't own a business. Yes. Or don't hire me. What? The number was 80%.
What?
What?
I mean, like upper, you know? Yeah, in the
1.1. What do you mean? 1.1 right here.
0, 1.1.
Oh, for the CDF.
1 over root 70. You gotta take the sample size into account.
Okay, so 0, 1.1. I got 1.
I'm so lost here.
Like, look.
Which part? Because they're talking because of me. All right, guys. Give me a second.
See, it's like 1.1, 1.17. So.
What the hell are you doing?
Well, you said.
Look. Your upper is 1.1.
Yes.
1 over the square root of 70. That's 70.
That is the square root of 7.
There's no square root symbol. How is that? Well, just do
Wait, but how do you get
1
that?
over the square root of 70.
I didn't know that. Make it a few more.
Frank, what's the problem?
Wait, but this is 79%.
My sigma is not 1, that was the original 1. But now it's 1 over the square root of 70. Okay, guys, question, honestly, future business owners who care about making money and not getting sued, would an 80% chance of success be good enough for you?
No.
So question, how much time would you be comfortable? Check the math, check the math. You're the statistician for this company. You're sending the people out. What number would you personally be comfortable with? In other words, check different numbers. You can always do inverse if you had in mind a probability that you'd be comfortable with. So is 90% your cutoff?
1.3.
Then you go to inverse norm. You start with 90% to the left and you come up with what the calculator gives you. What does it give you? I just did 1.2, by the way. I just went up to 1.2 and it gave me 95%.
Wait, what's the 1.1?
The original problem,
Yeah, I know, but like, where'd you get it from?
the book.
1.3.
Oh, I thought you like.
We did 1.3.
the number of hours that you had.
1.3.
Like an hour and 25 is 98%.
An hour, what is it?
An hour and 25 minutes.
An hour 25, that's 1.4 something.
1.3.
Hour 25 minutes is 4/10 of an hour.
Yeah, if you put 1.3, it goes to like 99.
Well, 24 minutes, it's 4/10, it's 4 6-minute periods. So 20, and then 25 minutes, like 1.4 something. 1.416 bar.
Is there a better way to find it?
Yes, well, what you can do instead is you first start with a probability that you're comfortable with. Maybe it's 90%, maybe 95%, maybe 99%. And you use the inverse norm, you work backwards and it'll give you the value. But remember, from a business owner's perspective, if you want a 99% chance that he'll finish, then there's also going to be a very high chance that you'll be paying this technician to wait around and do nothing. Okay, because 99% chance, it might be 2 hours per unit. And then on average takes an hour, 15 minutes, let's say, and now they're waiting around for 45 minutes per unit. So there's always a balance. Yes.
Just so to get for 90% to inverse norm, 0.9, 1 divided by square root of 7.
To the left, yeah, it should work. What do you get?
1.15.
1.15. So for 90%, that makes sense. Yes.
Wait,
Okay.
so we're not changing the n.
No, there's 70 units. You're not changing the n.
Oh.
How did you change the
I
n?
thought
There's-
the n was like the hours.
Oh my God. Yes. Probably not. Yes. No, not the center, left.
Why left?
Because it's to the left.
Oh, wait, how did it recognize that? So when I put center, it said error. How did it know that?
It did. So you did something wrong. What the hell you do? This is inverse norm, right? Yes. Area 0.99. U is not 1.1. U is 1.
Still gonna give you an error.
1 over the square root of 70. To the left. Okay, go away.
Go away.
Okay, so does that make sense? Question on that? Yes.
I would put that in a TI 83.
Yeah, you got me, kid. I just work here. I honestly don't know. I know how to use my TI 84. I tell other people, if you're gonna use other calculators, go on YouTube. Somebody has asked, somebody has answered it, whatever question you have. I just don't know the answer. Okay, I mean, if I had time, I might be able to figure it out, but I just don't know. Okay, Google, yes, question?
I was gonna help him out because he still has a normal CDF button, right? Do you have it?
Yeah.
So it's a certain order. So first you put negative 99999, and then you put the comma 1.0. You just gotta put the commas.
Okay.
You just gotta learn the order, bro.
Kind of learn the order, bro. Okay, bro. So, are there any questions on what we've done so far today? Yeah, so you got it all. Love it. So that concludes chapter 19.
Wait, that was like so much easier than 18.
Maybe the only reason it was easier than 18 is because you're using all of your knowledge from 18, which you've mastered by now because you've done all the homework on time. And therefore, because of that, 19 became simple. You ever think of that?
Wait, no, but the thing is.
No?
that,
Fair
you know,
enough.
If you want to compare the notes, like 18 is like 3 pages of notes and this like half a page.
Well, then in that case, let's go to chapter 20.
No, that'd be great. I wouldn't say that. No, because if you're gonna do more work that I don't want to do.
Did you really think I was going to end class at 7:30? 7:30!
Can we do another practice problem? Can we do another practice problem? Yeah, can we do like 3 more?
Fair, that's fair. The dog, look at the dog. Oh, look at the dog. That is like the most well-behaved dog like in the history of time. Yeah, we're all looking at you. Yes. Who's a good dog? Who's a, God damn it, look at me. All right, exercises 19. All right, do you want one? All right, I'll give you one. Shh. What?
We do a lot of practice problems and then the homework will be so easy. So that you don't have to start on 20.
Ooh, that's deep, man. All right, here's one for you. All right, here's one for you. Shh, please. To estimate the means, this is 19.27 in the exercises in the book, 19.27. It says, and I want you to stop me every time there's a piece of information that you feel might be useful to write down or to, notate. To estimate the mean score mu of those who took the MCAT on your campus, you will obtain the scores of an SRS of students. From published information, you know that the scores are approximately normal with a standard deviation about 6.4. Well, they gave me some information besides that.
It's normal.
It's normal. And the standard deviation is 6.4, but they did not give me the mean, at least not yet. I also know that I took an SRS, which I don't know if I specifically mentioned it before. I know I've mentioned earlier in the course, but I don't think I mentioned it today. All of our statistical tests that we're doing all require our samples to be SRSs.
And what if they're not?
Then you can't use the math. They have to be SRSs. They just have to be.
So all the problems you're gonna give us can be SRS.
Yes, if they're actually looking for math, if it's not a trick question or a question designed for you to say, sorry, can't do it because it's not an SRS, then yes, they're all SRSs. Okay, anytime you're doing math, it's an SRS. How large a sample must you take to reduce the standard deviation of the sample mean to 1? How large of a sample size must you take to reduce, or sample sizes must you take to reduce the standard deviation to 1? Thank you, I thought of it myself. So how large of a sample size must you take to reduce the standard deviation to 1?
He's locked you down.
There's no way I'm losing this one. So did it. It's who looks away first that counts. I will not lose this. I will not. I won! Yes! Yes! Yeah. Sorry, yes?
Do you want to round up for this?
No, I wanted that. It's a, well,
Or like,
it's a, yes, the answer to the question has to be a whole number.
okay.
Yes,
So
yes.
we don't know, well, we're trying to find like the 10, right? And then,
How large a sample size must we be?
so can we do like
They didn't give us like the new.
I don't need mu. I know I don't need mu because they didn't give it to me. Right? So it must be that I don't need it. If I needed it, they would have provided it. Or it's a mistake. All right, yeah, it could be a mistake. Yes? No, but I'm thinking if I can calculate, I don't need it either because I can calculate it. Yes?
For the X bar, right, that's what we're talking about?
Yes.
Okay, so for it to be one, would you need the denominator to be the same as the 6.4? So the square root of n has to equal 6.4, so it turns into 1.
Okay, so we know that sigma for x bar is equal to sigma for x over the square root of n. The sigma for the sample mean is equal to the sigma for the original divided by the square root of n. We want the sigma for the sample mean to be 1. We know sigma for the original is 6.4. So it's just a matter of solving this formula for n. So n is equal to something in the vicinity of 42.
Did they give us what?
Huh? I did say the vicinity of 42, did I not? Did I not say that? Yes. Huh? It's 40 point, oh, thank you so much for that. So 6.4 squared, 40.96, and 40.96 means that we take what for n? 41. Not because 41 is closer to 40.96, even though it is, but because if you look at the two numbers on either side of 40.96, 41 and 40, 41 will have reduced n more than 40 will. We'll just sigma. So the bigger the n, the smaller the number over here. So 40.96 is the value that we need to get it to 1. Anything less than that won't have reached 1. Anything more than that will have reached 1. And therefore the answer is 41. Yes? Yes?
How do you get 41?
I squared 6.4.
That's it?
That's it. Solve for n. If you have a fraction equaling to 1, the top and the bottom must be equal. Right? Give me a fraction equal to 1. Any fraction equal to 1. Go.
6 divided by 6.
Wow. Give me another one. You don't know any other fraction equal to 1. That's the only one that you know is 6 divided by 6. Can anyone else provide, please, a fraction equaling to 1? 5 over 5, 30 over 30. Huh?
That's extra.
3.14 divided by 3.14, which is close to pi over pi. Now, because of that, because 6.4 has to equal the square root of n, if you square both sides, 6.4 squared has to equal n. Hey, we're looking for n. So n is 6.4 squared. But wait a second, 6.4 squared is 40.96. You can't have a sample size 40.96. That does not make any sense. You can't ask for, don't look at me like that. He was so weird, this guy. So you can't have 40.96 people, so we go up to 41 people. Does that make sense? Yes? Okay, let's do another one. What? I just said, I'll say another one, yeah. What? I don't know who? DJ who? I don't know who that is. Is he? Can I see a picture of him, please? I just don't know if I should fail him or not. That's the question right now. It's a good-looking guy. He's nice and robust. Ah, yes. All right. All right, here's one. 19.31. About illegal gambling. Sounds fun. 19.31. Question reads as follows. Unlike Joe from the previous exercise, who we're not going to talk about, the operators of the numbers rackets can rely on the law of large numbers. It is said that the New York City mobster Casper Holstein took as many as 25,000 bets per day in the Prohibition era.
25,000 start.
Okay. 25,000 bets per day. Apparently. I'm sure he had people working for him. He didn't do it himself, but nevertheless. That's 150,000 bets in a week if he takes Sunday off. Yes. So that's 150,000 bets per week. No Sunday, because of course, it's the Sabbath and whatnot. Can't take bets on the Sabbath. So Casper's mean winnings per bets was 40 cents. 40 cents. How much? So the mean winnings per bet. I'm running what these things are because I don't know yet what values, what variables to assign. I'm not even sure what the question is yet. So everything that I write down, I am describing verbally what they are, so I know how to use them. His standard deviation for single bets is about $18.96. His standard deviation, well, that's sigma, is $18, what did I say, 96 cents? 96 cents. That means he wins, on average, 40 cents per bet, but the spread of how much he might win is $18.96 in either direction. So he could win $19, give or take, and lose 17, 18, whatever. That's just one sigma out. Could be two sigmas, could be three sigmas, who knows? Very small mean, very large sigma, comparably. What are the mean and standard deviation of Casper's average winnings on his 150,000 bets? So we don't care about this number for this problem. It's the 150,000 bets that we care about. So that's my N. 150,000 bets. The mean for any one bet is 0.4. The sigma for any one bet is 18.96. It says, what is the mean and standard deviation for the average of 150,000 bets? How much is he going to win on average if we take all 150,000 bets into account? How much is he going to win? What's the average value for each of those weeks?
40 cents.
40 cents. He still expects to win 40 cents per bet. What is my sigma for average, for the average X bar? How would I calculate that?
1/√.
I'm sorry, what? 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 So what? What? So what? What's by sigma X bar? What?
18.
What? What?
Bro, man.
What?
0.4?
Yeah, keep going.
Cents.
Would it be 0.4/18?
It's
No.
127.
How much?
Answer is 127.
What's the formula for sigma of X bar?
140 divided by 18.
No. What's the formula for my sigma of X bar? It's sigma over the square root of the sample size. Well, I'm sorry about that. I just thought it was funny to do so. And, you know, I was gonna say is, humor trumps education. So sigma x bar equals 0.049. But I do apologize.
So it's 0.4 over.
No, it's 18.96. It's the original
Then why did you say I
sigma.
was wrong?
I wasn't really listening to what you were saying. I just assumed you'd be wrong.
So
So, I'm Josh. Yes?
you just plugged in 18.96 over the square root of 150,000.
Yes.
Cool.
Cool. But I do apologize. No, I don't really apologize. The truth is that in my head, I was thinking it was 0.4 over root 150,000 because I mentally made a mistake. So if I didn't hear 0.4, I just stopped it immediately. And then I look back and I'm like, oh crap, it's actually 18.96 over whatever. Okay, so that means if you took all 150,000 bets, the average of those will be 0.4 with this standard deviation. That means if you do this for lots and lots and lots and lots of weeks, right? But if you do this for lots and lots and lots of weeks, then it's expected that the sigma of your averages week to week to week would be very small, which means you would expect basically, essentially, the same value every week. Which is what, by the way? How much are you gonna make per week? 40 cents per bet, which is 0.4 times 150,000, which is $60,000 per week. That was back in the day. At 40 cents a bet, you're like, 40 cents, that's nothing. But that amounts to 60 grand, huh? I know what you said. You want a run a numbers rocket? Seems like it's a good way of making money.
What are we gonna put?
Sure.
Can we bet in this, like gamble this class?
Sure. You're gambling for your grade every time you open your mouth. So I'm just joshing. Am I? All right, so what is the probability that his average winnings per bet will be between 30 cents and 50 cents? What is the probability that his average winnings per bet will be between 30 cents and 50 cents? Where are you getting that from? You're just making it up. We don't make up stuff here. So rather than actually, you know, thinking about it, you just set a random number. If it is 92%, that'd be really awesome.
95%.
You get that? I didn't do the math. You get that from?
I did.
Oh, did you?
Yeah.
Which button did you press?
CDF
Okay, what's your lower?
0.3,
What's your higher?
0.5,
What's your mu?
0.4,
What's your sigma?
up there.
Up there. Thank you for that. Can you be more specific?
0.049.
Yeah, 96.
Wow. 95.8%. 95.8%. So not too shabby. And that was quick too. That was quick. I'm impressed. Please.
0.3, 0.5, 0.4, 0.049.
Why is the lower one bigger?
Because the question was between 30 cents and 50 cents. 0.3 to 0.5.
It's also 2 standard deviations away. Why is that?
Thank you very much. Thank you. So, thanks. I'm gonna go Thursday. Oh, wait, today's Thursday. I'm out. Okay, so anyways, are there any questions?
Why is it is it a coincidence that it's exactly 2 standard deviations out?
It's not.
95%.
Oh, a coincidence.
Okay.
All right. All right, I am stopping this now. I will see you all next time.